All right, so similarly to how I kind of mixed things up for the charging second example, and the circuit was the same, but I kind of switched the capacitor and the resistor around. I want to do that same thing for the discharging case because something really interesting happens at the VX node. So let's go ahead and just draw an example here. Right, I'm going to put my capacitor here and my resistor here. And I'm basically going to say, okay, so I'm going to give myself just a 1 microfarad capacitor and a 1K resistor just to keep the tau pretty simple. And then I am going to let this source start at 10 volts and pulse down to 0 at time t equals 0, okay? And lastly, I'm going to label some nodes here. I'm going to call this one VS. I'll call this one VX. And of course, we know that the voltage across the capacitor is VS minus VX, okay? Or in other words, VX is VS minus VC, right? And so I need an initial condition. I'm saying I'm discharging the capacitor, so I'll let my initial condition here be that VC of time t equals 0 is equal to 10 volts because my capacitor is charged. And what I'm interested in is, like I was last time, what is VX going to look like? What is that voltage at that node going to look like over time? Okay, so let me just move all this down a little bit. And again, I'll draw 3 plots here because it's clear that in order to determine VX, we need to both determine VS and VC. And so let's go ahead and do that. Let me go ahead and make some plots here. I'll put one there, and then I'll make copies of it. Paste one here, and then one here. And I'll let this one represent VS of t. This one will be VC of t. And then this one will be VX of t, okay? And so we're interested in figuring out what does Vx of t look like. All right. And right off the bat, we can pretty easily identify what Vs of t is going to do. Like I said, it's basically going to start at 10 volts, right? And then at time t equals 0, it's going to pulse back down to 0 volts. And then it's just going to stay there for all time. And we also know what our VC of t should look like, right? Well, we know that VC of t for a discharging case is our initial capacitor voltage times e to the minus t over tau. And we know that this behavior, based on our initial condition starting at 10 volts, our VC of t should do this discharging exponential behavior right here. And that's according, of course, this behavior is according to this equation. That's important to just note. And so I'm interested in seeing what happens to Vx of t. Well, if I want to say that Vx is Vs minus Vc, I can see that what happens at time t equals 0 is very interesting, right? At time t equals 0, my Vs of t is equal to 0. And my VC of t, because it can't change instantaneously, is still equal to 10. Here, let me write VC of 0 is equal to 10. And so Vx of t at this time, right, all time before that, it's still Vs minus Vc. It's going to be 10 minus 10, which would be 0 all of this time. And then at time t equals 0, I have the source pulse low, goes from 10 to 0, and my capacitor voltage, instantaneously, it can't discharge, so it stays at 10 for that instant, which means that Vx of t goes down to 0 minus 10 or negative 10 volts right here. And then as this capacitor discharges, right, let me get my laser pointer out, as the capacitor starts discharging and that voltage starts dropping, then this capacitor, this node voltage starts rising each time. And so what we end up with is behavior that looks just like this. for node Vx, okay? So it's pretty interesting. It doesn't, I think intuitively, it makes sense if you analyze it, you know, instant by instant in time, right? So all time t after the pulse source goes low, that voltage is just 0. And so as this voltage drops down to 0, it makes sense that this would tend towards 0 as well. But it's this first instant where this pulses down to 0, so that Vs of time 0 is 0, and Vc of time 0 is 10, that we get this node to shoot down into the negative voltage range, and then basically bleed its way back up to 0 as the capacitor discharges. And then in the final state, the capacitor voltage is 0 volts, the Vx is 0 volts, and Vs is also 0 volts. And so everything's discharged, all the energy has been removed from the capacitor. And yeah, so that's this example. Our second discharging a capacitor example. Of course, it's probably not 100% clear to everybody. If you have any questions, definitely happy to answer them. And without any further delay, we are going to move on to our next type of component, or our next energy storage element, which is called an inductor. And so in the next video, in the next section of videos, I'll be talking about inductors. And then once we introduce inductors and talk about those, we're going to move on to RL circuits, which are very similar to RC circuits. Not exactly the same, but all the same principles apply. So now that we've done a bunch of RC circuits, we should be equipped to do RL circuits, and I'm excited to get started with that. So I will stop this video right here.